In this section, we look at an introduction to vectors in space in 3 dimensions. So here's a 3D vector in component form. We have v1, v2, v3. So we have 3 components as opposed to 1 per dimension. And again, we have the unit vectors. The I vector is the unit vector in the x direction. So instead of 1, 0, it's 1, 0, 0. We have the j vector 0, 1, 0. And now we have an additional k vector in the z direction, 0, 0, 1. And so this is the vector in component form. Here it is in unit vector form. And same idea with 2 dimensions in a lot of ways. If you want to find a vector, you can do terminal point minus initial point. Same idea as in 2 dimensions. Here are some properties of vectors in 3D, very similar to 2D. Vectors are equal if and only if corresponding components are equal. The magnitude is the Pythagorean sum of the components, though this time we have 3 components. To get a unit vector, you take your vector and divide by its magnitude. To add 2 vectors, add by component. Scalar multiple, you multiply in with each one. A dot product works the same way. You take the products of the components, pairs, and then you add them together. So finding a component form of a vector, we have initial point 342, terminal point 364. You subtract terminal minus initial. Here it is in component form. Then if you want to get a unit vector, you do the Pythagorean sum of 0, 2, 2. So rad 0 squared plus 2 squared plus 2 squared becomes 2 rad 2, and then you simply take your vector divided by its length to get the overall unit vector in that direction. Here's the dot product. Multiply the 4 and the negative 1, the 0 and the 3, the 1 and the 2, and then add up all those products. The angle between 2 vectors. Actually, just like in 2 dimensions, the cosine of the angle between the 2 vectors is the dot product divided by their magnitude, so that's no different. And again, if the dot product is 0, the 2 vectors will be orthogonal, that is perpendicular. If the dot product is positive, there'll be acute angle between them, and if it's negative, it'll be an obtuse angle. So that's no different than 2 dimensions. Here we have finding an angle between 2 vectors, 1, 0, 2, 3, 1, 0. Here's a 3D representation of that. And the dot product is on top, the magnitude's on the bottom. You get 3 over rad 50. Remember, to get these magnitudes, it's a Pythagorean sum. And you do the inverse cosine of that, 64.9 degrees. 2 vectors parallel. 2 vectors can be shown to be parallel a couple ways. One of them is if you can take a single scalar and multiply it to get the other vector. So you have an initial point 1, negative 2, 0, and 3, 2, 1. Make a vector, and is it parallel to these 2? Well, first let's get a vector for these 2 by doing terminal minus initial. So we get 2, 4, 1. Now to 2, 4, 1 compared to 4, 8, 2, if we multiply this by 2, we get 4, this by 2, 8, this by 2, we get 2. So these are going to be parallel, u and w. However, for w and v, multiply by 2, but the last one, 1 to 4, is not multiplied by 2. So therefore, w and v are not parallel. Okay, using vectors to determine whether points are collinear. Well, this is just like what we've done, but backing up one step. You have these 3 individual points, so find vectors that go between them. Just 2 of them, really. You don't need all 3 to connect them. So the vector from P to Q, we do Q minus P, we get this vector. You can do P minus Q, Q minus P, doesn't make a difference. And then P to R, we'll do R minus P. So we've got these 2 vectors. And now if we want to see if the points are collinear, we simply want to find out if these vectors are parallel. If the vectors are parallel, the points must be collinear. And let's see, multiply by negative 2, by negative 2, by negative 2. These are parallel vectors, therefore the points must be collinear. And you can see that represented visually here. All right, terminal point of a vector, you give an initial point and a vector. To get the terminal point, simply add the vector to the initial point. So 4 and 3 is 7, 2 and negative 1 and 1, negative 1 and 6 is 5. The vector acts as a translation, so it just takes the point, moves it accordingly, so you just add this vector to your initial point component by component to get the terminal. All right, this is weights in 3 dimensions. I'll leave this here a moment for perusal. Again, sort of a rehash of what we saw with 2 dimensions. Okay, more examples. We want to find a unit vector going from negative 735 to 0, 0, 2. So first we need to find the actual vector, so we subtract. We do, the vector v is going to be 0 minus negative 7, 0 minus 3, 2 minus 5 to get to this one. Then to get the, we want to get the magnitude, so it's the Pythagorean sum. So rad 7 squared plus negative 3 squared plus negative 3 squared, that's equal to rad 67. And then finally to get the unit vector, we've got to take our vector divided by its magnitude, and here we are. In this one, we want to find the angle between these two vectors. So we have our formula. Theta is the inverse cosine of the dot product of these two. So multiply, 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 and then add those, divided by magnitudes. And so we have here inverse cosine of 5 over rad 60, which is 49.8 degrees. Over here, we want to find out if these two vectors are parallel, orthogonal, or neither. And so we'll try a dot product, and we get 2 times -1, -3 times -1, 1 times -1 is 0, so therefore they're orthogonal. We know they're not parallel, obviously, well, before even knowing they're orthogonal, because to get from 2 to -1, you multiply by -1/2, and clearly -3 to -1 or 1 to -1 is not that same ratio. In this case, we wonder if these 3 points are collinear. So again, we find vectors joining 2 of them. So A to B is this vector, and then we'll do B to C is this vector, and then simply find out if these vectors are parallel or not. If they are, the points are collinear. So to see if they're parallel, to see if you can take a number to multiply to get the same thing every time, I just divide each component set. So -3 over 2, is that the same as 2 over -1? Is that the same as 4 over -2? Well, these guys are the same, but not the same as this one. So therefore, these vectors are not parallel, and consequently, the points are not collinear. We have an initial point, a vector, and we want to get the terminal point. So to get the terminal point, we simply add the vector component by component, and there is our terminal point.